Hello, this is Nachum Danzig, and welcome to Computer Architecture. I'm a teacher at the Jerusalem College of Technology. Today we're going to discuss the single cycle MIPS implementation, and specifically how to run or how the computer executes three instructions. How it executes the load word instruction, how it executes the R-type instructions, and how it executes a BEQ, a branch if equal instruction. So let's get started. General notes, some of these diagrams are simplified, and we'll see more detailed diagrams in other videos. We have previously, in previous videos, discussed various components like the register file, the RF, and the instruction memory, and the data memory, and the ALU, and how it's constructed. We didn't discuss exactly the sign extension and the shift operators, but they're rather simple. All those components that we've discussed before, we are going to combine them in creating the data path for the MIPS single cycle. We didn't explain the main controller and the ALU controller, which are two control units in the data path, in the layout, in the architecture of the MIPS chip, and we'll discuss those also in the follow up to this video. Okay. Now, some important things to keep in mind is that we can only use each component, each part of the computer once per instruction, because we can only use any instruction, any component once per cycle. And since this is a single cycle, we have to do the whole instruction in one cycle, which means we can only use each component once in that cycle, which means once in the whole instruction. Because of this, we're going to have separate data memory and separate instruction memory, which are going to be essentially two access points to the memory, two different access points to the same memory. Kind of like a large box that has two windows at the top, two trap doors at the top to open up and look into the box. They're looking into the same box, but there's two different trap doors that open in. One of those trap doors is the data memory access, or the data memory unit, and the other is the instruction memory unit. Similarly, we're going to see that we have extra add units, and here we'll see here's the data path right away. So we see here, for example, well, here's the controller. Here is the RF, that's the register file. That's where right in the middle here, that's where all of the registers are, which means if we want to read the value in a memory in a register, we're going to have to put the values on the input lines here, the read register 1 and read register 2, and get their values out of these two exit lines. And if we want to write, we'll use these input lines over here. Now, that's the register file. Here's the ALU. Here is the data memory, which means our access point to memory for data. That's what we're going to use in a load word command if we want to load from the data from our array into a register. So we need a data point. We need an access to the data to do that, and that's this data memory unit. We also have the instruction memory unit, which is the first thing we're going to do, which is to read the instruction from memory. Because remember, all the instructions of our assembly code are sitting in memory of the computer, in the RAM memory of the computer, and we need to read one by one each instruction. So that's also a kind of reading of memory. So we have this instruction memory access point to the memory. Notice that the instruction memory has only has no control units. In other words, it's only for reading. Whereas over here, the data memory can be either a read or a write. Because if it's a load word, we're going to read data. But if it's a store word, we're going to write data to a location in memory. So we have to be able to tell this memory unit, are we reading or are we writing? So that's this line on the top. If it's a 1, then it means we're writing. And if this line on the bottom is a 1, it means we're reading. But there's no similar lines here on the instruction memory because we're only going to read from when we're reading an instruction, we're never going to write an instruction. We're only reading what the programmer wrote. We're not writing the program. We're reading the program. Okay, so this is the basic layout. We'll get to the details of what each part does when we examine the different commands. First thing but first let's talk about this central controller here. This is the central controller, and this is the ALU controller. And basically the instruction opcode, which is instruction bits 31 to 26, that's the leftmost bits, that is going to tell the controller what command it is. And based on that, he will know what lines here to turn on and what to turn off. Like I said before, for example, if it's a load word and we're reading from the memory, then this mem_write line will have to be a 0 and this will have to be a 1. So for each command, all these lines, all these exit lines, will be either 1s or 0s depending on what the command is. And that's what the controller's job is. So the controller receives 6 bits of input. That's the opcode, which is bits 31 to 26 of the command. Based on these inputs, its logic gates produce various output lines. So, for example, here I have the output lines as they should be for various commands. If it's an R type, it's only the register destination, the register write, and the ALU op1 should be lit up, should be a 1. All the others should be a 0. If it's a load word, so notice that the mem load word is I'm going to read from memory, so the mem read is 1. Yes, I'm reading, but no, I'm not writing. 0 on the mem write. What else is 1? Register write, because I'm loading a word into a register, so I'm writing to a register. Mem to register, well, we'll see what that does. ALU source, we'll see what that does. And the rest are 0s. So similarly, for the other commands, we have 1s and 0s according to what the control lines settings should be for that command on the controller. Notice the X's here, that's like a don't care. The ALU operation over here, I have a little table that tells you what it means. If it's 0, 0, it means add. If it's 0, 1, it means subtract. And if it's 1, 0, it means it's an R type, and it's not saying what it is. It's still up in the air what the command will be, and we'll see how that works when we get to an R type. But basically, these ALU op commands are telling the ALU unit whether to do add or subtract, or not telling it either if it's an R type. Okay. So let's look at the load word command. Now, over here, here's the load word command. Here are the 1s and 0s that have to be lit up. First, but let's look at what the command is. Just to remind ourselves, the command is built like this. Remember, every command is 32 bits of data. So the opcode is the leftmost area, and that's 34. 34 is the opcode for load word. That's you can look up on a table or the MIPS green card. You're not going to memorize that, but that's the opcode for load word. Then we have the RS register is and the RT register. In other words, this could be 8 and this could be 9, which would mean T0 and T1 would be the registers that I am writing here. But what does it mean? So here's how you write the command. If you wrote a command, you'd say load word from RS with the offset, in other words, indexed into the array, whatever the immediate value is, that's these 16 bits over here. Take the RS, which is here, and then add to whatever its value is, add to it these 16 bits after they've been sign extended. And then that will be the location memory I want to read. And where am I going to write to? I'm going to write to RT. That's what this command means over here. And here it's written out. The RT, the register file, the R means here register file. The register file at place RT, at location RT, that register, should get the value of the memory as specified by the register value of RS plus the sign extended by 16 bits of the immediate value. This is a 16-bit immediate value. We've got to extend it by another 16, so it's a 32-bit, so we can add it to this register. That's just a review of what the load word command does. That's how it's supposed to operate. Now, how is the data path, how is the MIPS chip going to get that accomplished? So the first thing we're going to do is we're going to look at these ones and zeros, the ALU source, for example, mem2 register, and we're going to copy those into the data path. So that's what we do here. So, for example, this is the load word control signals. So, mem to read is a 1, mem to reg is a 1, ALU source is a 1, reg write is a 1. Those are the 4 ones that we saw over here. 1, 2, 3, 4. Notice I don't mention the zeros, but all the others will be zeros. So we're going to read this diagram from left to right. So the first thing is that the PC has the value. Remember, the PC is pointing to which instruction is the next instruction to run. So the PC is pointing to our load word. But we have to read it. So we have to go to memory at the location that PC is telling us and take it out. So we put that into the read address of this memory thing. And what's going to be spit out here on the right side is the value at that location, which is also going to be 32 bits. But that'll be the instruction. And that'll be our load word, which again looks like this. In other words, it'll be the 34 will be the highest, the leftmost bits, and then it'll be the RS and the RT. And that's exactly what we see over here. We see, well, it's hard to see here, but there's lines coming out. And what we're saying is that the instruction 31 to 26 bits, those are the leftmost bits of the instructions, which is 31 to 26, going straight into the controller. Now, the controller, based on that, will eventually push out these values. In the follow-up to this lecture, I'll explain how. But for the moment, let's just assume that he knows how to do that. But that didn't happen yet. We're still over here on the left. Everything in the left here is happening at the same time. But the first thing that happens is the instruction just starts coming out. And the opcode goes over here. The bits 25 to 21 go onto this line, which is the RS. And then 20 to 16, it goes on this line, that's the RT. The RD is going to go onto this line, even though there is no RD in a load word. Remember here, there's an RS, RT. The RD would be like this area over here, these bits over here, but they're really just the immediate value, the index of the array. And so it's irrelevant, but there are bits there, and the hardware is built to work for all commands. So it doesn't know that this RD is really garbage. It's really not the real value. Is not relevant in this case. So, but those bits start going here. And if you notice, 15 to 11 go here, but also 15 to 0. That means the whole immediate value goes down on these lines. So we have some splicing going on. In other words, some of the lines are coming out and turning here, and there's a little dot here, this black dot, which means not only do those lines go this way, they continue also this way. So we're sort of, you can imagine an electrician cut the wire and added another piece and spliced in a new wire. So there's two, so it forks. So the electricity goes both ways at the same time. That's what's going on over here. What's going on up here? The PC, in addition to going into instruction, is going to this add unit, which has a hard-coded 4 over here, which means the result here will be the PC plus 4, which actually, if you think about it, is the next instruction. Because remember, every instruction is 4 bytes from the previous instruction. So if we add 4 to whatever the PC value is, we'll be pointing to the place in memory where the next instruction is, and that gets us ready for the next command. And that eventually is going to make its way all the way around here and back into the PC register. This is a PC register, and it's going to be, the new value of the register will be here. Without explaining these parts here, it'll eventually get through here and back to here. So that's what's happened in the first stage. that's called the instruction fetch stage. And we've read the instruction, we've fetched the instruction, and we've also incremented the PC. The next stage is, well, that the controller actually gets the command and starts to think about, in the second stage, he's already producing the values which will be used in the third stage, these values. Also, the register file is reading in these registers and producing output on these lines. It hasn't yet reached the ALU, but the output of these lines will be whatever the RS is here and the RT is here. The RD is still kind of irrelevant because we didn't get data to write yet. We may never get, whatever, we didn't get data to write here. But this RS and RT have produced outputs over here, which is our RS and RT, which we're going to need. Also, we've assigned, the immediate value has become sign extended to become a 32-bit value. Well, that's very relevant because remember, we have to take our load word has to take the immediate value and sign extended by 16 bits. So we've done that. We've taken this immediate value and we've turned it into a 32-bit value, having the same value, but just we put sign bits to the left. So if it's a negative, we put ones over there. And if it's a positive, we put zeros over there. It didn't change the value of the number, but it made it into a 32-bit number. So that's what we did right here. And that's going to be very important for us because we take that value and we want to add it, if you recall, to the RS. That's what it says over here. Add it to the RS, the register value of the RS. So let's do that. Well, the RS is coming into the ALU. How can we get this sign extended value to come into here? Well, on this multiplexer, on this mutex, on this, no, multiplexer, I was right, first time. On this multiplexer, we have to put either a 1 or a 0. Well, if you notice, there's a 1 at the bottom here, and that 1 means that the lower arrow will get passed through the multiplexer because only one of these two values will get passed through. This is kind of like a gateway. Both values are coming in, but only one gets to go through. Which trapdoor do we open? Well, that's what this line tells us. And since the ALU source has a 1 on it, which by now we know the controller has produced that 1, now this lower value, which is the sign extended, will go through, and not what value? And not the RT. The RT, which is sitting here on this line and coming into this multiplexer, is going to get stuck. It's not going to go through because I have a 1 on this line and not a 0. If I wanted the RT to go through, I'd put a 0 here. But I don't. I want the immediate value, which has been sign extended, to go through. So now I've got the full sign extended immediate value into the ALU, and I've got the RS, and I need to add them. So this ALU controller needs to tell it to add. Well, does it? If we see, it's 0, 0. ALU operation is coming down on this line and telling the ALU 0, 0. What does 0, 0 mean? If we look back over here, we see 0, 0 means add on this little box over here. So we are, in fact, telling it to add. So now we get the value out over here on this line. That is the result. By the way, we've done some other things over here. We've also taken this sign extended and shifted it left and done some adding with the PC, but that is for our branch command, which we'll see later. But it's happening in parallel. We're just not interested in it. You know, it's going to happen, but we're going to throw that value in the garbage. In other words, there's going to be a value there, but it's not going to make it through this multiplexer. But just understand that it's happening in parallel, this branch chain, this branch action, this adding for the branch command. But here we are in our load word, and we're adding over here, and our value comes out over here. Now, if you notice, this value in the next stage, in really the fourth stage, is being put into the data memory. Well, does that make sense? Well, yes, it does. We want to load something. That value that we got is where to go in memory. So that's where to go in memory to read to then later put into a register. Which register? The RT. So we're going to read here, and that's going right into here, and that's perfect. And where will that value come out? It'll come out in the read data value. But wait a second, we can only read if this memory is set to read and not to write. Well, what is it set to? Well, it's set to 0 on the memory read, but on this line, it's a 1 on the memory write. So that's perfect. So we have the right values here to make it read. Now it comes out over here, but this multiplexer better be set to 1, otherwise it won't continue on its way. And is it set to 1? Yes, it is. Memory to register is set to 1. So therefore, the value that we read now in the memory at the offset plus the index, at the offset plus the pointer to the array, will come out here and go down this line all the way up and to the right data. Perfect. We want to write this data to a register. And it's sitting there waiting to be written. But which register should we write to? Well, we're going to write to whatever register is on the register write input line of the register file. What are the possibilities? Well, there's two possibilities. Either it's the RT coming into this multiplexer, or the RD coming in. Now, wait a second. We just got through explaining that there is no RD. There shouldn't be an RD. So we better use the RT, and that's what it says here. We're writing to the RT. So we better take the RT. So let's go back to our picture and see that we need to take not that this is the RS, this is the RT, this is the RD. So we'll take the RT. We better have a 0 on this multiplexer. Let's see, do we? We go up, and there's a 0 there. Somebody nicely wrote in a 0 for us. Oh, that was yours truly. But there's a 0 there. So that means that we will, in fact, write to the RT the value that we chose to do. And there's the value that we got out of the memory from over here, which came through. And that was all because this multiplexer was set to 1. And that was all because this ALU source was set to 1, which let the sign extended value go in here and not the RT. And we also have to mention that the register write is set to 1 over here, if you notice. Because otherwise, this value would come to the register file, and if this register write would be a 0, he would hit a locked door. He would say, sorry, the register file is not allowing writing at this time. But we've set register write to 1. So it will get written. So we've accomplished everything we need to do. We have now seen how a load word can go through here, given that it has the right control digits on these control lines, and it can produce the result that a load word is supposed to. It also incremented the PC, which it was supposed to, and we're done. Now, I should point out that the first two stages, we don't yet know what the operation is, right? We only know what the operation is once the controller reads it, but actually reading it from the memory, we're going to do even before we know what the operation is. So we always do that. And we're also going to add 4 to the PC. We always do that. And we're also going to send it to the controller, and we're going to read 2 lines from the, 2 registers from the register file always, even before we know what it is. So in the first 2 stages, we do the same behavior for every single operation, because we have to. We don't know what operation it is yet. Only in the 3rd stage have we deciphered it, and we are able to depart and do different actions based on what the operation is. So these lines won't get lit up until the end of the 2nd stage, which means they'll be ready for the 3rd stage. All right, let's do another command. And we'll do the add instruction. Now, the add is of the type R. It's an R type. And R type, I always like to say, is called R because it has lots of register. R stands for register. It's the one with the most registers. It has the RS, the RT, and the RD. Notice there's no immediate over here. There's a function code over here, which is going to be very important. The shift amount I'm not going to discuss right now. It's not important here. RD is the destination. And the RS and the RT get added together. See, the RS and the RT are added together and assigned to the RD. Good. So bear this in mind that we have to use the RS, the RT, and put them into the RD. Now the order here, RS, RT, and RD, is good to understand because it's always the order when you look at the diagram. So let's look at the diagram. So again, I put the lines in. Notice I put ones and zeros here. How did I get there? Well, it's really from over here. Just a second. For an R format, the register destination, for example, is 1, unlike the load word. And there's some other ones. There's a total of 3 ones. Let's see if I did it right. So register destination, you see, is a 1. And there's 3 ones. There's register right over here. And the opcode is 10. Now, what does that mean, opcode is 10? That's actually critical to understand in a R type. So if we go back over here, when it says 10, that means R type. In other words, when the ALU op is 10, it's an R type. So what does that mean? What it means is that I'm not telling the ALU controller whether I want to do add or subtract. How will the ALU controller decide what to do in that case? So if you notice, he's getting another input, and he'll use that input to decide. He's basically saying, when there's a 10 over here, it says, ignore what look over to the left and use that input as your way of deciding whether to tell the ALU to do add or subtract or anything else. So where are they coming from? They're coming from instruction 5 to 0. 5 to 0 is the 6 rightmost bits. That, my friends, is the function code over here. So the function code will be telling it what to do. So, in other words, for an add, there'll be a certain function code over here. And that will tell it to do add. So let's go back. Again, like we said, it's going to be the same thing. The PC is going to increment it by 4. I'm going to read the instruction. It's going to come out onto these lines. It's going to go into the controller, but the bits are not yet ready. It's also going to read 2 registers, and it's going to assign extend the entire lower half of the instruction, 0 to 15, even though this is not useful for us at this time. But we don't know that it's not useful for us. In other words, it's going to take all of this RD, shift amount, and function code and view it as one block and shift and sign extended and put it to 32 bits. But that's meaningless for us in this command. But remember, we did it for the previous command for the load word. But we're going to do it again. We're just going to ignore that information. We're going to do it. The hardware is sitting there, so it's like the electricity flows into this sign extended and it comes out, and there's nothing we can do about it. But it doesn't cost us anything because it's happening at the same time as we're reading these registers. So we read these registers and we got the RS and the RT on this line. And what do we need to do? We need to add them together. So, well, we have great news because the RS is coming into the ALU to be added, but the RT may or may not be coming into the ALU to be added, but we want it to. So we better have on this multiplexer, we better have the value 0 to tell it put the RT in and not whatever this sign extended thing is. So it is in fact a 0. See, ALU source 0. So we're going to get the RS and the RT in here. And this sign extended that gets happened over here just goes nowhere. It hits this multiplexer and never gets further. The ALU, meanwhile, has been told by the instruction here 10 to look at this, and it knows to do add. So great, it's doing the add. And now this add value is going here and going into the address to read memory. But this is an add command. We don't want to read any memory. So it's sort of, so we're not interested in reading memory here. So, well, we'll see, where else does it go? It also goes down here and straight into this multiplexer. Well, that's the value that we want. Remember, this is an add. So it's like essentially we did 7 plus 5, and we want to have a 12. And we don't want the 12 to go into memory. We want 12 to be our number that we're going to put into the RD. So it's sitting here on this multiplexer. Now, which number better be written here? In order for that 12 to get through, better be a 0 over here, and not whatever came out of memory at location 12. Now, if you notice, it's actually written here that it's a 0 on read and a 0 on write, but really you can't do that. Really what it's going to be is it's going to be a read. In other words, I mean, it's really a don't care on the read. It could be a 0, but it could also be a 1, because even if we do read from memory, it won't get any further. Main thing is we better have a 0 on the right, because we don't want to write anything to location 12. That would not be our purpose here. So just showing you that what these bits are here, what these control lines should be. It says that here that they're both 0, and that's perfectly fine. But it also could be that the read is 1, is all I'm saying. Because even if I did attempt to read, it wouldn't get past this multiplexer because there's a 0 on this line, which is going to take the result of the ALU directly and pass it along all the way down here and up to the register read. And where do we want to write it? To the register write. To the register file in the write data location. And where do we want to write it to? Well, that's the data we want to write, but where do we want to write it to? We want to write it to whatever is the right register, which is the RD we want. But if you notice, there's two possibilities again. There's the RT coming in and the RD coming in. So which one should be let in? It should be a 1 over here to tell me that I want the RD to come in. And if I follow this line up and I see, oh, register destination is a 1. So it's correct. A 1 over here will cause the RD to go through. The RS and the RT came through here, were added. Then the result was passed along by this multiplexer because it was 0, and it went into the register file and got written. So we did. We wrote 12 into RD, which is what we wanted to do. And again, the ALU op is 10 to tell it to look at the function code, which will tell it add. Now, actually, I have a table of the function codes that might be worth looking at for a second here. If you see, here's an add. The ALU operation we saw is a 10. The opcode was a 0. Yeah, I sort of I misled you a little bit here. When it says over here, when it says over here 32, this is a mistake. This 32 should be a 0. Remember, all R types are 0, and the function code should be 32. So let's maybe put in parentheses. There. This I guess I should really write opcode, and it's a 0, and a function code is 32. So that's what we see in this other table down here, that the opcode is 0, the function is 32, and the 32 is what tells, when the 32 comes in as the function, it tells the ALU to spit out 010. And 010 tells the ALU controller to do. It tells the ALU unit to do an add. In other words, again, over here, there is a 32 coming in here in the function code, and coming out here is a 010, and 010 tells ALU to do add. If it had been a 00 on this line instead of a 10, then the ALU also would have put out a 010. And you can see that right here. For example, if it's load word, the function code is irrelevant, but he also needs to, it's a 00 coming in, right? Not a 10. And he's also going to put out a 010. 010 means do add. So you see, there's lots of ways to get the ALU controller to tell the ALU to do add. You could either do a load word, a store word, an add, unsigned, and an add. So these are all the possibilities for these commands. In other words, this would be this is where the opcode is. These are not R types, so the opcode is not 0. And then the function is irrelevant, but this number 35 already tells it 0, 0, which means put a 0, 1, 0. And the add is going to be the opcode is 0. The 32 is the function code. And the function code is going to tell the ALU controller to put out 0, 1, 0, which tells the ALU to do an add. So that's what happens over here. The ALU controller puts 0, 1, 0 and tells it to do an add. And we have added the two registers. Remember, over here was a 0, so that the RS came through. We added them, we put them through here, and we wrote it. So that is the R type. Now we have the branch, which is perhaps the most confusing, but actually one of the quickest. So let's see how the branch works. The branch is opcode 4, and it takes the RS and the RT and the 16-bit immediate. And what does it do? It takes the 16-bit immediate, it sign extends it, it adds 2 zeros. See that? Because if it's a branch, we're jumping to a new place in memory. In other words, we're reading a new instruction, and which means if we were on instruction 1, we're going to instruction 10. But remember, every instruction is 32 bits, which means they're each offset from each other by 32 bits, which means 4 bytes. Which means if we want to go from instruction 1 to instruction 10, we're actually going to have to go 40 bytes forward. So the way we do that is by shifting left 2 spaces. Because any number that you have in binary, if you shift it left once, it's doubled. And if you shift it left twice, it's doubled twice. So that's doubling twice is times 4. So what we do is we take the 16-bit address and we add 2 zeros to it. So if it was like, let's say 10 over here, it'll become 40. And then we sign extend it to get a 32-bit address. So it tells us how much to add to the PC. So we sign extend it, then we take the PC and we add to it this number plus 4, which just means we take the PC after the increment. Remember, the PC is always incremented by 4. So we take the PC plus 4, and we take the immediate after it's been multiplied by 4 and turned from 10 to 40, let's say, and then we sign extend it to the 32-bit number, and then we add it to the PC plus 4, which is also a 32-bit. So we have 32 bits plus 32 bits. We're going to get a 32-bit number, and that will be our new PC if and only if the values in RS and RT are equal. That's what this means. That's the BEQ. So here's the RS, RT. We're going to compare them if they're equal, and then we're going to change the PC to be whatever this value is. So how do we do that? So again, we're going to have to copy these 1s and 0s from the table that we had before. And what we see is that the instruction will get read. The PC will get incremented by 4. So we've already done the PC plus 4. Then we are going to put the RS and the RT into these register files. And hopefully we're going to get both of them out over here. So what do we need to have on these lines? We want to compare them. How do you compare two numbers to see if they're equal? Well, the best way is to subtract one from the other. And if the result is 0, if it's 17 minus 17, it's 0. So the result is 0, and that means they're equal. If it was 17 plus 17 minus negative 17, so it would be 34, and it wouldn't be 0. So only if the numbers are exactly equal, 17 and 17, then I'll get 0. So I want to put them into here and do a subtract. So actually, opcode 01 on ALU op tells it to do subtract. let's double check that. BEQ, this is subtract. The 0, 1 on the ALU op is going to tell the ALU controller to spit out a 1, 1, 0 to the ALU, which is going to tell it to subtract. So over here, the 0, 1 is going to tell him to put out, what was it, a 1, 1, 0 to tell him to do subtract. He's going to subtract. Now, he's going to subtract the RS and the RT, but in order for that to have worked, this multiplexer has to have a 0 on it, and it does. See, the ALU source is 0, so that's the 0 is going to come through. So we have 0, which means the RS is here and the RT is here. We're subtracting them. Now, the result will be, let's say, 0 over here, or it could be any other number. But actually, we don't really care about the result. We care just if the result was 0, yes or no. So we have a special line coming out of the ALU called the 0 line. And the 0 line is a 1 if the result was 0. And this is true if the result was 0. But if the result was false, if the result was, let's say, negative 17 or negative anything or positive anything, then the 0 line will be 0, false. So look at this 0 line. If it was true, then it goes up to this AND gate. And this AND gate has a permanently coded in a 1 over here, which says that which is the branch line, which means that it is a branch command. It is a branch command, and we want there to be if there's also a 1 here, because they were both equal, then we'll have a 1 and a 1. 1 and 1 is 1. So that means there'll be a 1 on this line. Now, what will this line be choosing? It'll be choosing this. Well, what is this? This is an add, and I wrote here for branch. So what is it? Well, notice that the PC plus 4 is coming along here and coming right in here. Okay, that's our PC plus 4, which is what we want to do. We want to add the PC plus 4 to the offset that he gave us. Well, where is that offset? Where's that coming? Where's the other thing? So that is the 16-bit immediate over here coming into the sign extended. It becomes a 32-bit. That was the immediate value. That's instructions 0 to 15. And then it becomes 32 and it goes up, 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 and it goes into the shift left 2. The shift left 2 is going to multiply by 4. So if it was 40, first we sign extended it. Sorry, it was 10. We first sign extended it, and now we shifted it left 2, it became 40, and that's exactly what we want. 40 plus the PC plus 4 gives us the new location where the PC should be for the next instruction, where it should read the next instruction. And now, since there's a 1 on this line, that will continue through here. Now, in this multiplexer, there better be a 0 so that they will continue through this multiplexer. And there is, because it says jump line is 0, and that's the controls over here. So it's a 0 again, and that causes this line to go all the way to here and to write to the PC. So we will write to the PC the immediate sign extended, shifted left 2, multiplied by 4, value we'll write to the PC if and only if the RS and the RT, when we subtracted them, gave us an indication that they were equal, which meant that the 0 line was lit as positive, yes. So that is the BEQ. Okay. Next lecture, I will explain the controller, how it actually produces these signals. But that should give you an introduction for at least 3 commands in this single cycle. Other commands, work similarly. But this diagram may not fully explain how they do, in fact, work. You could work out how the jump works here. Some of the other commands should also work here, but not necessarily all of them. Okay, good luck. I hope this is helpful to you. See you in the next video.